This is the start of chapter 19, which discusses the structure and reactivity of aldehydes and ketones. We know already that an aldehyde has one R group and one hydrogen atom around a carbonyl, and that a ketone has two R groups around a carbonyl. Some simple examples of aldehydes include formaldehyde, acetaldehyde, and benzaldehyde. Some simple examples of ketones include acetone, acetophenone, and benzophenone. There are also many compounds found in nature and those that are made commercially that are more complex than these. For nomenclature, for aldehydes, what you want to do is take the parent compound and add the term Al, or Al for aldehyde. When you go from hexane to the carbonyl compound, the aldehyde, it becomes hexanal. When you have a ketone, you take the parent and add one for ketone. When we go from hexane to the ketone form, if the ketone is at the 2 position, then it is implied that the numbering position is 2. If you don't have to use the number 2, you just say hexanone, or you could call it methylbutyl ketone. But if you move that carbonyl to position number 3, now it's not implied what position the carbonyl is at, so you have to call it 3-hexanone or ethylbutyl ketone. Both are acceptable. When you prepare aldehydes and ketones, these 2 next slides are a reminder of what you already know. This slide discusses preparation of aldehydes. The first way to prepare an aldehyde is to oxidize an alcohol, and we can do this using PCC, DMP, or COCl2. These are from chapter 12. We can undergo an ozonalysis of an alkene. You know this from chapter 8. And then lastly, a hydroboration oxidation of a terminal alkyne yields an aldehyde as well. So these are all 3 ways to make the same terminal, or the same aldehyde. In the preparation of ketones, we have 4 different methods that we've already discussed. The first is the oxidation of secondary alcohols. So here we use a reagent sodium dichromate with sulfuric acid and water. We know this from section 12.10. We know that the ozonalysis of alkenes with ozone followed by dimethyl sulfide yields acetone. And then a third way to yield acetone from the starting material, the propyne, is the acid catalyzed hydration. And here we're using sulfuric acid with mercury sulfate to get to that more substituted enol, which tautomerizes to become the ketone. And lastly, we just learned that the Friedel-Crafts acylation reaction is another route to produce ketones. Here I've got an example with benzene and installing a methyl ketone. The reactions that we're going to discuss in this chapter are all examples of nucleophilic addition reactions. These are reactions to the carbonyl carbon, and carbonyl carbons are electrophilic because of the difference in electronegativity between the carbon and the oxygen atom. The resonance form that you want to draw here has a positive charge on the carbon and a negative charge on the oxygen because oxygen is more electronegative than carbon, and that gives that carbon electrophilicity. When a nucleophile attacks a trigonal planar carbon atom is transformed into a tetrahedral sp3 hybridized carbon. When we compare the reactivity of aldehydes and ketones, we see that aldehydes are more reactive than ketones. Why is that? The first reason is steric effects. Ketones are more sterically bulky than aldehydes. And the second reason is electronic effects. Ketones have more electron donating groups, which makes them less electrophilic. Here's a practice example. Which molecule is more reactive to nucleophilic addition reactions? Take a moment to pause your screen and think about the answer to this question. The compound on the right is more reactive to nucleophilic reactions because not only do we have the inductive effect of the carbonyl oxygen atom, but also these trifluoromethyl groups are pulling electron density away from that carbonyl carbon. So this carbonyl carbon is especially more reactive than in the molecule acetone. Our last slide focuses on nucleophiles that react with carbonyl carbons. We have oxygen-based nucleophiles such as water, alcohols, and ethers. We have sulfur-based nucleophiles that have hydrogen sulfide and this dithiol, which reminds me that we should add to this list ethylene glycol and this glycol with an R substituent to this list. Also for nitrogen atoms, we can have the primary and secondary substituted nitrogen atoms. Then a reminder of what we already know. We remember that from previous chapters that that carbonyls can be reduced with aluminum hydride and borohydride. These are going to be lithium salts and sodium or lithium salts in these cases. We also know that Grignards can be used to react with carbonyl carbons, and we'll see that also nitriles can be. And then we'll look at a reaction called the Wittig reaction, and this is an interesting way to install carbon atoms in the place of carbonyl carbons. This is going to be the harder of the reactions to learn, in my opinion. And these are all the content of the remainder of the chapter, which is going to take us 2 more lectures to cover. That is the end of this video. Have a great day.